Hi, everybody. Today we're going to be opening up a new topic, and that's charges in motion. So, up until now, we've been talking about charges that are fixed points in space, like what is the electric field at this point due to a charge positioned at this location? What is the force between two charges stuck in one place, right? Well, now we're going to take a look at what happens when charges are in motion, and we're going to look at it in the context of circuits. So in this chapter, we're going to be covering all the sections, and the goals of this chapter are to understand why these moving charges are important to us. That's going to be pretty easy because all of our technology relies on moving charges. We're going to also look at the meaning of current and drift speed, and also examine the relationships of voltage, current, and resistance. We're going to look at some rules to help us analyze circuits, and we're going to analyze a circuit that has both a resistor and a capacitor in it. So take a look at these sections that you may need to review to best understand this chapter. I wouldn't worry too much about drag force in fluids. What I would do is make sure you have a really good understanding of electric field and potential difference and the relationship among charge, voltage, and capacitance. So this first section is just a motivation for our study. Charges in motion, it's really important. We use it all the time in technology, and we also use it to get our brain to work for us. So charges are sent back and forth through neurons in the brain. And you probably already know, maybe even better than me, that your brain is full of electrical signals, and that's how parts of your brain communicate with each other. So those electrical signals, those are molecules, but those molecules have electrons bound to them and certain charges, right? So it's pretty interesting study here, looking at charges in motion. So we're going to define some new quantities. One of them is called the current. Okay, it's just a rate of change of charges, and we'll talk about that. And then we'll also really examine batteries, okay, from a new perspective. We're going to also analyze simple circuits. So what is electric current? Electric current is the rate at which charge flows. So where does current come from? In a typical circuit like this, the current comes from a battery. So a battery sets these charges into motion by providing a potential difference, right? And we know potential difference is related to energy by U equals QV. So a potential difference will give charges energy to move in a circuit. What is this battery and how does it work? This is pretty interesting stuff. So a typical battery, like an alkaline battery, it's made of a bunch of chemicals, and some of these chemicals like to hold on to electrons. For example, the anode, okay, this purple material right here, it's made of zinc oxide, and it is a material that likes to hold on to electrons. And then we place in between the anode and the cathode, which does not like to have electrons, a material that does not allow conduction, in other words, an insulator. So it doesn't allow those two electron holders and electron deficient materials to touch. And that's important because when we connect this battery to a circuit, we want to establish a potential difference. We don't want the two parts of the battery to have the same potential. So what you do is you hook up one part of your circuit to the little centerpiece on the top, and that's the positive terminal. And the positive terminal has a positive potential because it's lacking electrons, right? It's deficient in electrons. and then you hook up your other side of the circuit to the negative part of the battery, which holds all the electrons, right? And because these are connected to each other, the electrons are going to sense a higher potential and get motivated to move this way. So the battery has two terminals, and we attach our device and our circuit to those two terminals and cause the current to move. So using the language of the previous chapter, we would say that the positive terminal of the battery has a high potential and the negative terminal of the battery has a low potential. And that causes electrons to move. Here's another way where we can understand why those charges move in the wire. And this is from an electric field and force perspective instead of a potential perspective. The potential difference between the battery terminals means that there's an electric field within the wire. And if the field points along the length of the wire from the positive to the negative terminal, then a mobile charge will feel a force F equals QE due to that electric field. And if that charge is negative, it's going to point in the force is going to point in the direction opposite to E. And if that charge is positive, then it'll point in the same direction as E. So we have a movement of charges. We've established that a battery gives these charges energy or produces an electric field that gives these charges a force to move along the wire. And the way we characterize the movement of charge is through the current. So the current is the rate at which charges flow past any particular point in the circuit. So a current in a circuit is given by delta Q over delta T, where delta Q is the amount of charge that passes through a certain point, and the delta T is the time it takes to flow past, those charges flow past that point. So the units of current is the ampere, and it's named after a French scientist and a mathematician. 1 ampere is 1 coulomb per second. We're going to talk initially in this chapter about currents that are steady. And that means that the current value I is the same no matter where you are in the circuit. Okay, so I is constant, in other words. And you may have seen us use current I with an arrow next to it, and it's not to be confused with a vector. So current is not a vector quantity. The arrow is simply to illustrate what direction the current is flowing. The direction is described by either clockwise or counterclockwise motion. So in this case, with the positive terminal on this side, the negative terminal on this side, this current would be flowing in a counterclockwise direction. If instead you were to flip the terminals of the battery, then the current would flow in a clockwise direction. So something interesting is going on here, and I sure hope it isn't confusing. It definitely was confusing to me when I first started studying this. I remember it clear as day. The direction of current by convention is chosen to be the direction in which positive charges flow. So if you remember my explanation earlier, I was always saying that those charges are electrons, okay? The electrons are moving. And that is physically what is happening. However, the way we describe current is we describe it as the flow of positive charges, and it's simply by convention. You can blame Benjamin Franklin again for this. The interesting part of it is, when he was studying current, he actually didn't know what was making up the current at the time. He had no idea electrons or atoms even existed. That was well before the time where we had the ability to see subatomic or atomic level things. So Benjamin Franklin just was recording his observations, and he decided to define this positive terminal and negative terminal, and then the fact that current would flow from the positive to the negative. Okay? But in reality, if you were to have a little, subatomic microscope and look at current, what you would actually see is little electrons moving to the right. Okay? But since the electrons are moving to the right, they're leaving behind positive charges, and you can think of those as being what is moving to the left. Okay? So we are going to be, whenever we define current and its direction, it's going to be the movement of positive charges, where those positive charges are leaving the positive terminal and going to the negative terminal. So we all know that the charge of an electron is very small value, right? 1.6 times 10 to the minus 19 coulombs. So currents typically are really small. For example, 1 coulomb is an enormous amount of electrons moving past a certain location every second. It's 10 to the 18 electrons. So that's an enormous amount, and typically currents that exist in devices and in your brain, in nature, are very, very small. They're on the order of, microamps to nanoamps. So let's kind of, think about that value, how many electrons, right, in 1 coulomb per second. Let's think about it physically, like what is going on. So if we have a wire and we kind of like select one cross-sectional area of that wire to start counting current charges passing through it, okay? In 1 second, 6.25 times 10 to the 18 electrons would pass through that little section, okay? Would go from this side to this side. 6.25 times 10 to the 18 electrons per second. So that's what current is, right? Current is counting how many charges pass through one particular place at a unit time. So let's take a look at this example. In this example, we're going to charge a sphere using current. Okay, so we have a sphere and it's hollow and it's electrically isolated, which means it's uncharged, okay, and it's not gonna get charged by touching anything else. So if we have this sphere and it's isolated, so the only way it's gonna get any charge is if I connect a wire to it and send a current down that wire. And so that's what we're gonna do. Let's say we send a current of 5 times 10 to the minus 6 amps through that wire. How long would it take for the sphere to hold a potential of 4 times 10 to the 5 volts? So the value of the current is 5 times 10 to the minus 6 amps, okay? So that's the rate at which the charges are going through that wire. And how does that... So, if this is charge per second, how does charge relate to potential? Right? How does charge relate to potential? So we have to think back. So charge relates to potential through this equation, right? KQ over R. So once we establish this relationship of how much charge is required to give us a potential of 4 times 10 to the 5. Once we know how much charge, we can calculate how much time it takes for 5 amps to give us that much charge. Okay, so that's kind of the order of operation. So we're going to find Q and then use I to find delta T. So this is maybe something that we didn't go over specifically in lecture for chapter 17. I will just tell you the result now. So if you have a sphere, the value of the potential at the surface of the sphere is identical to the potential produced by an electron that is a distance of r away. Okay, in other words, V, we know this, right? V of a point charge is equal to kq over r, right? Where r is the distance from the point charge and q is the point charge. Well, V of a sphere, that doesn't look like a V, is also kq over r, where r is the radius of the sphere. So you can see they have the same equation. And so you can imagine the potential of a sphere at the sphere's surface as being the same potential as if a point charge was located at the center of the sphere. So I'm just explaining to you why this is a valid equation to use to find the potential on the surface of that sphere. So we're told that the radius of the sphere is 0.15 meters. So, it's my dogs, sorry. So we have our potential is 4 times 10 to the 5 volts. Okay, our Q is unknown, and then our radius is going to be 0.15 meters. So let's solve for Q so that we can find T, delta T. So Q is going to be 4 times 10 to the 5 volts, 1.5 meters divided by K, which is 8.99 times 10 to the 9. So the charge comes out to be 7 times 10 to the minus 6 coulombs. So that's how much charge is required to create a potential of 4 times 10 to the 5 volts on the surface of that sphere. The rate at which we're moving the charge is 5 times 10 to the minus 6 amps. So if we are moving 7 times 10 to the minus 6 coulombs of charge, how much time will that take? We can find that out. Delta T is going to be 7 times 10 to the minus 6 divided by 5 times 10 to the minus 6. That's going to give us units of seconds. And that comes out to be 1.4 seconds. So in other words, it's going to take 1.4 seconds for us to charge up the sphere to a potential of 4 times 10 to the 5 if we're charging it at a rate of 5 microamps. The trickiest part of this problem is understanding the relationship between V and Q. Once that's figured out, unit analysis can pretty much take you the rest of the way through the problem. So I want to talk about a really interesting concept, and that's called drift speed. So the current I tells us what quantity of charge flows past a certain point per second, right? Let's see how this relates to the actual speed or the average speed at which the charges are moving through the wire in the circuit. So to understand drift speed, I'm going to take a qualitative or conceptual approach. The next few slides take a more mathematical approach, and I'm just going to skip that for now. I don't think it's really going to be useful to us. We have a lot to cover in this chapter. I think I have a really good analogy that's going to help you understand what drift speed is. Okay, so we're going to skip through this. And then what I'll do is I'll do a unit analysis to prove to you that this current is proportional to drift speed. Okay? So doing all this derivation here, right, gives us the following equation. That current can be defined also as the number of charges per unit volume times the cross-sectional area where we're tracking the current passing by, the magnitude of the charge of each of those charges, and then finally this value called the drift speed. So let's look at the units and then I'll explain what drift speed is. And let's convince ourselves that all this stuff on the right-hand side actually does come out to be coulombs per second. So N is the number of mobile charges per unit volume, okay? So that would be a number over meters cubed, right? Where number doesn't have a unit, it's actually blank, so I'll just leave that as the number 1. A is a cross-sectional area, so that's meters squared. E is a charge, Q, or C, right? Coulombs. And then finally, a speed or velocity is meters per second. So you can see that these meters combine to meters cubed, cancel out with this, and what we're left with is coulombs per second, which is the units of current. So now that I've kind of convinced you in my own way that this is how we express current, let's talk about what drift speed is, okay? Drift speed is not the same as the speed at which each individual charges move. And that's because there's a bunch of charges moving all together, right? We saw that 1 coulomb per second was like 10 to the 18 electrons. Okay, so there's a lot of electrons packed into a small area. So these electrons, they bump into each other, okay? Their motion is actually really random. They're bumping into each other, they're bumping into the edges of the wire, and it's gonna take them a little bit of time to move through the wire because of all these collisions. And you can think of it like a swarm of bees, okay? So in a swarm of bees, you have a bunch of bees creating a swarm, and they're all like buzzing around, right? And they're probably individually buzzing really fast inside that, in that swarm. But the hive itself, or the swarm itself, I should say, is not moving if very, very fast at all, right? If you're trying to get all of those bees to move a mile away, it's gonna take a long time to get them all in sync moving, right? So that's analogous to the drift speed. So the drift speed of electrons would be the speed at which the collective group of electrons would move. And it's going to be slow because of all those collisions that the electrons are having with each other and with the edges of the wire. So drift speed is actually quite slow, in other words. Here we can calculate the drift speed of a flashlight. It's done in your pre-lecture video. Let's just scroll to the answer and you can see the slowness that I'm talking about. The drift speed is, I mean, barely a tenth of a millimeter per second, okay? So it's like, why? How is that even possible? How are we able to turn on this flashlight in an instant if those electrons are moving so slow? Well, drift speed is slow because, you know, those electrons are constantly colliding with everything. And the reason why you're able to turn it on so fast is because the electric field that's set up when you put the flashlight on, it gives the force to those electrons and allows them to propagate in the wire close to the speed of light, okay? So although the electrons are drifting around, there's always some at all points in the circuit, and the ones that are really close to the light bulb are going to move very quickly to the light bulb and thus turn it on. So let's define qualitatively some other interesting ways we can use current. So objects or devices that run off of batteries, they are direct current circuits, which means the current is moving in one direction, okay? The direction would be given by current leaving a positive terminal and entering a negative terminal, right? This is a direct current, one direction. Now, there's another way we can power devices, and certain devices like toasters or lamps, anything that you plug directly into the wall is going to run on alternating current. So our house wiring is actually done in alternating current. And what is alternating current? Alternating current is alternating the direction of the current per unit time, okay? So if you look at maybe the back of a toaster, or if you look maybe even on the little bricks that you have to plug your phone into to charge it, you can see some writing on there. Right now I'm looking at a 12-watt USB power adapter by Apple. And it says that, gives me the model number, and then it says that the input is 100 volts to 240 volts, 1.5 amps, and then there's a frequency at the end. It says 50 to 60 hertz. So it's expecting me to input an alternating current that alternates at a frequency of 50 to 60 hertz into this device. And what comes out, if you keep reading, it says output 5.2 volts, 2.4 amps. So, and it has like a symbol that looks like this, a straight line with a dash. That's the symbol for DC. So actually to charge your phones, you use DC. But since we don't have DC coming out of our walls, we have this little brick thing that is going to convert the AC coming out of our walls to DC in order to charge your phone. So alternating current, it comes into play when we need to move massive amounts of voltage with little heat. And so we're going to learn about the power that current can generate in a little bit. But for now, just to kind of give you a reason why we use alternating current, because maybe that is kind of, you're thinking about that right now. Why do we use alternating current? Well, by switching the magnitude of the current, we can actually cool it down, since we don't have electrons moving in the same direction constantly, right? Here in direct current, the electrons are constantly moving in the same path. And so that's going to warm up this area. But if we are switching them from one way to another way, it actually reduces the heat that they generate, because you're turning them around and moving them in another direction. So another interesting aspect to alternating current and to our household electricity is, if you look at a plug, you will notice that there's 3 holes, and what the function of them I'll explain. So the first 2 holes in your outlet are responsible for being the positive and the negative side of your circuit. And the 3rd hole is there in case there is an overload of current, and this is called the ground, and it gives the current a safe place to go in case there is an overload, in case there is a short in the circuit or something faulty goes wrong and you need a place for the current to escape, versus the current maybe blowing up your light bulb or jumping to something nearby. If you have, curtains or something flammable nearby or something conductive nearby, it'll prevent it from jumping over there. Instead, it gives it a nice place to go. So you'll notice that some devices don't have a place to plug in the 3rd hole. Like, for example, many of your phone chargers, and that's just because the current flowing through is not that high. But anything that sends massive amounts of current will have that third prong for safety reasons. So let's get into how we describe alternating current. So alternating current, you kind of looked at it and maybe you recognized it's a sinusoidal function. So we use sinusoidal functions to oscillate the current direction, right? In other words, to change the current magnitude from a positive to a negative. And it turns out that the current and the voltage are proportional to each other. So this graph could actually represent either one. They're both going to change at the same rate. And so let's recall how we describe sinusoidal functions. The amplitude of the function is this green line right here. The period is from peak to peak. And the period T is inverse of the frequency. In other words, the frequency of the oscillation is 1 over the period. That's frequency. Here, F is in units of hertz, which is inverse seconds. If we want to convert that to angular frequency, we multiply F by 2 pi and get omega, which is the angular frequency. And the angular frequency has units of rads per second. This is an interesting graph, right? So I was reading the numbers to you on the back of my iPhone charger, or I think this might be my iPad charger. And it said 50 to 60 hertz, right? Well, all over the world, we use either 50 or 60 hertz. And this graph here kind of tells you which uses which. And all over the world, you actually can also use different amplitudes of voltage as your main electricity source in your homes. So in the red area in North America and the northern part of South America, we typically run on 120 volts, 60 hertz. But in other parts of the world, mainly runs on 50 hertz and a higher voltage of roughly 220 or 230 or 240. And so that's why when you visit other countries, sometimes you need an adapter to plug in your devices. And that's because the electricity in the buildings and homes are powered by an alternating current that runs at a different amplitude and a different frequency. So just to put some numbers down with our kind of mathematical analysis of alternating current, right? If we run at 60 hertz here in America, that means that the period or the time it takes to go from a positive current to a negative current is going to be about 1 over 60. Okay, so every 1 over 60 seconds, which, let me put that in my calculator, right? 1 over 60 is about 0.016 or 0.017 seconds. You're going to have your current change from a positive value to a negative value, okay? So let's take that idea and look at this conceptual question. So suppose that part of the wire in the flashlight example was only half the thickness of the rest of the wire. Okay, so the initial thickness was 512. Okay. And now we have a slightly smaller or narrower wire that is 256 millimeters. Compared to the rest of the wire, okay, meaning compared to the thicker part of the wire, what would the current in the thinner part be? So what happens to the current if we decrease the thickness of the wire? So let's write down the equation we learned for current as a function of drift speed and cross-sectional area, right? So it was N, cross-sectional area, charge of the moving particle, and the drift speed. So you may be inclined to automatically draw this relationship between A and I and say, oh, well, if A increases, then I is going to increase, or vice versa, right? But let me remind you that before we looked at this equation, we defined the current through a circuit to be constant at all points of the circuit, okay? So even though we have a circuit that has a thin area and a thick area, okay? Let's just pretend that's a thicker wire, right? So even though we have current flowing like this from a thick area, through the thin area, through the thick area, that current value is going to be the same everywhere on the circuit, okay? So the current itself is not changing at all. It's going to remain the same. okay? Why? Because, so let me cross this out, right? We're not going to use that relationship because this concept overrides it, the fact that current is constant over every part of the wire. But something in this equation does change, and we'll see that in the next got the concept. But current is constant at all points on a wire in a circuit. So let's think about this again, except the drift speed. Let's see, how does the drift speed change? So it's down our equation again, NAQ drift. Okay, and we know that I must remain constant, right? I must remain constant. So if we examine the area and the drift speed together, okay, if one increases or decreases, then the other must do the same in order to keep I constant, right? So if the cross-sectional area is decreasing, well, then the drift speed is going to have to increase to keep I constant. Does that make sense? So let's see how much our area is changing. So we're dealing with a circular wire. So the cross-sectional area of a circular wire is a circle, right? Area of a circle is pi r squared. So our first r is, let's compare, I guess, the larger one, right? So it's going to be pi times 0.512 millimeters squared. And then we're going to compare that to our second thinner one. And then let's take the ratio of them to kind of see, compare them together. So the ratio, if you kind of plug it in your calculator, or maybe you can see it, because this is technically 2 times 2.256, right? But go ahead and put it in your calculator if you need help visualizing it. You're going to see that A1 divided by A2, 512 squared divided by 256 squared gives me 4. So A1 over A2 is 4. Okay, which means A1 is 4 times A2. And so if A1, okay, we're decreasing, right? So we are going, basically A2 is A1 over 4. So we're decreasing our area by a factor of 4. So then our drift speed must go up by a factor of 4. Right? If we're going down in our area by a factor of 4, then we must increase drift speed by a factor of 4. And so, therefore, our drift speed must go 4 times faster to account for that shrunken area. Okay? So the main concept here is that I is constant throughout the entire circuit, and it doesn't matter if the area changes, right? I has to be constant. That's an overarching concept here. So that makes this one kind of a trick question, right? But then you can see, well, it kind of makes sense when you look at it now, and this got the concept problem is I remains constant because even if the wire dimension changes, what changes to account for that is the drift speed. It's going to either increase or decrease in order to keep the current constant. So to wrap up this section, right, we kind of defined current in 2 different ways. One is current is simply the change of charge per unit time. Another way is the current is the number of mobile charges per unit volume times the charge of those charges times the cross-sectional area they're passing times the speed of the drift, right? The speed of the electron swarm moving through the wire. So those 2 are equivalent so that you can set them equal to each other. And I think you have to do that in one of your homework problems. So Current can be defined in those two ways. The unit of current is ampere. Current has a magnitude and a direction, but it's not a vector. The magnitude is given by delta Q over delta T or NQAV drift, but the direction is either clockwise or counterclockwise. All right. And then by convention, thanks to Benjamin Franklin, current is in the direction in which a positive charge would move. Okay, but in metals, typically it's electrons that are moving, but we're just going to pretend that they're not, and that it's the positive charges that are moving. And then finally, we took a look real quick at AC and DC current, right? DC means one direction, so it's either always clockwise or always counterclockwise. And alternating current continually changes direction at a rate, 50 or 60 hertz. And we can describe that direction change by like a sinusoidal function.